Okay, now we want to talk about the Newton-Gregory interpolation. So in Newton-Gregory, for us to do the Gregory interpolation, the first thing you have to know is how to construct a finite difference. How to construct a finite difference table. You cannot do Newton-Gregory interpolation if you don't know how to construct a finite difference table. So we shall be seeing how to construct a finite difference table. Then after that, you have to know how to expand the binomial. That is the binomial series. You must understand the binomial series using the factorial notation. How do we deal with that kind of series? How do you expand a binomial expansion in the Maclaurin series? And that is what we normally refer to as the binomial series, isn't it? Well, so if you have that binomial series, 1 plus x raised to power n is 1 plus nx, the first two terms, isn't it? Then the third term, when you have 2 factorial, then 2 terms in the numerator, x squared, like that, in that order. How do we form that binomial series from the Maclaurin's expansion? Are we together? Now, after that, after the binomial series, we shall now see how do we get the interpolation. How do we construct? How do we construct an interpolation polynomial? How do we construct an interpolation polynomial? Or how do we form an interpolation polynomial? Construction or forming are the same things because we apply maybe the series. So when you are applying another concept to get another one, it may be forming or constructing, isn't it? So how do we form an interpolation polynomial? Because sometimes you will be given you'll be told this is a cubic polynomial, and you'll be given certain values that x values are this, the y values are this. Then you are told to evaluate that polynomial at a certain value of x, maybe find f of 24. And if you look at this 24 is not in between. You're not in between the range you've been given. Maybe the x values you've been given from -1 or -1, 0, 1, 2, 3, 4, then followed by y value. So if you see this x value, because this is f of x, meaning you'll be told x is 24. So you'll be told to evaluate this function when x value is 24. And if you look at your finite difference table, you see 24 is not among these values, these are outside the range. Are you seeing that? So the moment 24 is outside the range, meaning you must have an interpolation polynomial. How do you construct or form that given polynomial when it is outside the range? So when it is inside the range, maybe you've been given a table like this, and you'll be told x values, then f of x value. X values -1, maybe 2, maybe 4, 6, like that. And y values you've been given maybe 12, maybe 120, maybe 140, maybe 210. You've been given this, and you've been told this is maybe a cubic polynomial, something of that kind. Then, from here, you'll be told to evaluate maybe f of 1. So if you are told to evaluate f of 1, meaning when x is 1. So you can see 1 is between -1 and 2, meaning that value of x is 1 is in between here, isn't it? So how are you going to evaluate when the x value is in between here from there? So we'll be using the forward difference formula. So how do we use the Newton-Gregory forward difference interpolation formula? Then maybe if somebody comes again and tell you to evaluate f of 5. If you look at f of 5 is between, x value is between 4 and 6, isn't it? So you see 5 is here. So it means for you to evaluate the point when x equals 5, you use the backward difference formula. So how do we deal with the Newton-Gregories? How do we deal with the Newton-Gregories? How do we deal with the Newton-Gregory forward difference? The forward difference interpolation formula. Forward difference interpolation formula. When should we apply the Newton-Gregory forward difference interpolation formula. Because there are instances when they will tell you using the Newton-Gregory forward difference interpolation formula, meaning in that case it will be automatically that value was ahead, so you're moving forward. Then sometimes they will tell you using Newton-Gregory's backward difference interpolation formula. You know, there are cases when they will be specific, but there are cases where they will just say, use Newton-Gregory's interpolation to evaluate maybe f of 1 in Roman 1 and Roman 2 to evaluate maybe f of 6. And if you check f of 1 at point when x is 1, you'll see maybe it's ahead here, so that you have to use the forward difference formula. Are you seeing that? And if you see f of 6, if you check where the x value of 6 is, you see it is up there. It is towards the end there, so that you have to come back, meaning you have to use the backward difference formula. So it means there are cases where they will not tell you to use the forward difference formula or the backward difference formula. It will be upon you to see where x lies, so that you are able to deduce that it is only forward difference formula which can evaluate this. You will be able to look at the table and see it is only the backward difference formula which can do this. Are you seeing that? So how do we deal with the Newton-Gregory's? How do we deal with the Newton-Gregory backward difference formula? How do we deal with the Newton-Gregory backward difference interpolation formula? So we are going to see all this. So the first thing is the construction of the finite difference table. So the finite difference table has nothing to do with, the construction of the polynomial, it has nothing to do with the forward difference formula, it has nothing to do with the backward difference formula. Meaning this finite difference table is used for all this. Are you seeing? So it means during the construction of a finite difference formula, you should not take in mind any of this. It is what uses that table. So this should not gear you on how to construct the table, meaning the table is independent from this. Are you seeing that? So it means at the point when you constructed the finite difference table, is now you can use it to form the interpolation polynomial, you can use it to evaluate the value of that polynomial using the forward difference interpolation formula, you can use it to evaluate the value of that polynomial using the backward difference interpolation formula. Let us start with the construction of the finite difference table. How do we construct a finite difference table? How do we construct a finite difference table? Now, to construct a finite difference table, I will use a case, an example, to see how to construct a finite difference table. So let us maybe consider a table from a polynomial. You'll be given this table like this. You'll be given a table, and in this table, you'll be given a table with some few values. One, two, three, 4, 5, 6, 7, 6. So here we have x and f of x. So you'll be told the x values maybe start from -1, 0, 1, 2, 3, 4. And the f of x, you'll be told when x is -1, f of x, you'll be told maybe it's 4, maybe it's 10, maybe 12, you'll be told it's 18, 24, and maybe 36. So you've been told maybe f of x is a cubic polynomial. You've been told f of x, for instance, is a cubic polynomial. So when you are told f of x is a cubic polynomial, they are trying to tell you that the highest power you should reach is power 3, isn't it? Are we together? So before we go to that instance, let's just put it open, without considering whether it is a cubic polynomial or a polynomial of higher order, isn't it? So for you to construct a finite difference table, this is what you do. For you to construct a finite difference table, this is what you do. You count how many values do we have here. 1, 2, 3, 4, 5, 6. We have 6 values. So for you to construct a finite difference table with 6 values, you multiply that 6 by 2. So you must have 12 rows. Are you getting that? These are how many values? 1, 2, 3, 4, 5, 6. So 6 values constructing a finite difference table with 6 values, you multiply that 6 by 2, meaning you must have 12 rows. Are you seeing that? Are we together? So you come here and you form a table with the 12 rows. You form a table with the 12 rows. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, I now have my table with the 12 values. I now have my table with the 12 values. So you know, not with the 12 values, I mean with the 12 rows, because the values are 1, 2, 3, 4, 5, 6. So those 12 rows, meaning the last value will only occupy 1 row, so the remaining 1 row will occupy by the title. Are you seeing that? All these 6 values, why we are multiplying 6 by 2 to give us 12, the last value will only have 1 row, meaning the remaining 1 row will be occupied by the title. So the title here, we have the x value and the f values. We just put aside, we know it is f of x, but just put aside, isn't it? So the x values, the first x value is -1. Are you seeing that? So once you write -1, you skip 1. You skip 1. Then the next is 0. Then you skip 1. Then the next is 1. Then you skip a row. Then the next is 2. Then you skip a row. Then the next is 3. Then you skip a row. Then the next is 4. So are you seeing the reason why I'm saying the last value will only occupy 1 row, but the first value has 2 rows, this and the one you skip. Are you seeing? The second value is this and the row you skip. The third one and the row you skip, 2 and the row you skip, 3 and the row you skip, meaning the last value 4 is only on this row. Are you seeing what I was trying to imply? So, constructing a finite difference table is the beginning of solving any problem with the Newton-Gregory interpolation formula, whether it is forward difference or backward difference, or you want to get an interpolation polynomial. Are we together? Now you put the f values. When x is -1, you'll be told f of x is. When x is 0, you'll be told f of x is. When you'll be told x is 1, f of x is 12. When you'll be told f of x is 2, f of x is 18. When x is 3, f of x is 24. When x is 4, f of x is 36. So you have transferred the data you've been given into the finite difference table, isn't it? Are we together? Now the finite difference, the difference at each and every interval is represented by a delta. So here, if you want to get the first differences, you denote it with a delta. Are we together? That delta is used to denote the difference, the changes. So you can see when you are getting the gradient, you are getting change in this, or change in this, the change in something when it was denoted by delta. Are you seeing that? Are you together? Yes. The change in something. If you want the change in y, so you are putting delta y over delta x to get the gradient. So that delta is usually used for the change in something, isn't it? Are we together? Now when you are looking for a change in something, what do? So it is always the second value minus the first value. When you want the change in something, it is like the final minus the initial, isn't it? So that if you get the change to be negative, then you say it was a decrease, isn't it? If you get the change to be positive, then you say it was an increase. But when you're looking for a change, it is always the final minus the initial, or the second value minus the first value. So it means when I want the difference between these f values is what we are interested in. The difference in these f values 4 and 10. It is the second minus the first. 10 minus 4, I get. Are you seeing what I'm trying to imply? Meaning if here I had 10 and here I had 4, it is 4 minus 10, I get negative 6 because it is the second value minus the first value. So it means what you are getting here may either be positive or negative. If this value is small, then it will be negative, isn't it? Are we together? So when you are constructing this finite difference table, it is the second minus the first, like final minus initial, isn't it? Then here the next one here, the difference between these two values, it is 12 minus 10. Then you have 2. So are you seeing you are now recording them in this row you left blank? Are you seeing what is happening? Then you move to the next one, you move to the next two values is this. So the next two consecutive f values is 12 and 18. Are we together? So it is second minus 5. 12 minus 18 minus 12 you have 6. Then you move on, the difference between these two values, 24 minus 18, 6, isn't it? Then the difference between these two values, 36 minus 24, you have 12. So you see, you found the first finite difference. Are we together? The difference is denoted by the delta. So if you want the second difference, you go to the next column. So if this is delta, meaning the next one is going to be delta squared. It's going to be noted as delta squared. Then you continue with the same process. So we are looking for the difference between these two values. So you see, 2 and 6. It's now 2 minus 6, you get? 2 minus 6, negative 4. Are you seeing you are writing in their middle? So you see the reason why you have to skip one row. Are we together? Then if you go to the next two values, 2 and 6, it is second minus first. 2 minus 6 minus 2? 6 minus 2? 4. Then you move to the next one. The difference between these two values, 6 minus 6? 0. Then you move to the next one. The difference between these two values, 12 minus 6? 6. Meaning you are done with the delta squares, the second row of the differences, isn't it? Then you move to the next one. It's going to be delta what? Delta? Delta cube. So in the delta cube, what do we have? The next changes. So you move here. We have negative 4 and 4, isn't it? So second minus first. 4 minus negative 4 is 8. Then here, 0 minus 4, negative 4. Then the difference here, 6 minus 0. It is always the second minus the first. Are we together? Then you move again, the next column. Until you reach a single value, it means you reach the end of the differences, isn't it? Or they will tell you it is a cubic polynomial, meaning you will just reach delta cube to show that when you are going to get that polynomial, you are going to reach, you are only interested in reaching the value where x is going to be cubed. Are you seeing that? Are we together? Are we together? Yes, so it means you are moving to delta power 4, isn't it? So start again. The difference between these two values, negative 4 minus 8. My friend, concentrate here. Negative 4 minus 8. Negative? Negative 12. Then here, second minus first, 6 minus negative 4 is 10. You go to the next column. So the next column we have delta power 5, isn't it? So you can see the next column is actually the last one because we are going to remain with a single value, isn't it? Are we together? Yes. You are going to remain with the single value. So we have 10 minus negative 12, 20, 22. So once we reach a single value, meaning we constructed the whole finite difference table. So are you seeing the first thing you have to do is to construct a finite difference table, and you've seen the procedure of constructing a finite difference table. Are we together? Now, after constructing a finite difference table, the next step, we need to know how do we form a binomial series. That binomial series where we add 1 plus x. That binomial series when we add 1 plus x raised to power n. How are we expanding this series, isn't it? Are we together? So how are we expanding this series when it was 1 plus, meaning when power is n, it is only the powers of x which will increase, which will decrease. But the power of 1 raised to power anything is just 1. That is why only power of x will be there. Are you seeing? Because there are two values inside here, meaning if you are getting the first term here, it is n combination 0, then maybe 1 raised to power 0, or maybe 1 raised to power n, x raised to power 0. So you were putting the powers of x to increase, the powers of 1 to decrease, 1 raised to power n. So 1 raised to power anything will be 1. So you will see, we'll only be having x only. Are you seeing? When this first value is 1. Can you recall that from the binomial? Are we together? Yes, so that there, if it is 1, the next one will be n combination 1, then 1 n combination 1 raised to power n minus 1, x raised to power 1. 1 raised to power anything is just 1. That's why you will not be seeing the 1s there when this value is 1, isn't it? You will only be seeing the ascending powers of x only with the respective coefficients. Is that okay? Are we together? Yes. So, when we were constructing, so we are done with the finite difference table, we are now in the binomial series. We are moving stepwise. The binomial series. So the binomial series of 1 plus x, when you are expanding 1 plus x raised to power n. What were you getting? Remember, it is the powers of x which are increasing. So remember when you add x factorial was implying what? It is x into x minus 1 into x minus 2 into x minus 3 into x minus 4 factorial. That the way you reach is where you put your factorial. Factorial will go up to 0 factorial, which is 1, isn't it? Are we together? Yes, meaning if you have 5 factorial, it is 5, 4 factorial, it can be 5 times 4 times 3 factorial, or it can be 5 times 4 times 3 times 2 factorial. Where you reach is where you put the factorial, but you know the last one will be 0 factorial, isn't it? Are we together? Now, if you look at what I've written here, if you have x factorial, this will be the expansion of an x factorial. So here, when we are looking for the first term, at the first term, the first 2 terms, it was 1 plus nx, isn't it? Why was it 1 plus nx? Meaning you are starting, when you have 0 factorial is what you are starting from, isn't it? When you had 0 factorial, there was no term in the numerator, isn't it? When you had 0 factorial, there was no term in that. Then our x is raised to power that 0, isn't it? Then you moved on. When you add 1 factorial, it means there was 1 term in the numerator, isn't it? Are we together? I'm not supposed that is just for x, but actually I'm expanding for n. So when I'm expanding for n, and I want to talk about n factorial, isn't it? Because I want to, in this example, I'm making a case of n. That was just for an explanation of the case of expanding a factorial. Are we together? Because it is this n factorial we want to deal with, isn't it? So when I'm expanding n factorial, what do I have? N into n minus 1 into n minus 2 into n minus 3 into n minus 4 in that order. When it is x factorial, the same way I placed, isn't it? Because here I need the n factorial, because n is the power, isn't it? Are we together? So if you have 1 factorial, it means there is only 1 term in the numerator. So if you come here, that only term is what? 1 is what? N. And then your x is raised to power that 1. Then plus the next, if you have 2 factorial, remember you're starting from 0 factorial, 1 factorial, you are now going to 2 factorial, isn't it? When you have 2 factorial, it means there are how many terms in the numerator? 2 terms. And which terms are those? It is n and n minus 1. We have n and n minus 1. Then our x is raised to power that 2. Are we together? You saw how this was coming about in the binomial theorem, isn't it? Then the next one plus after 2 factorial, when we have 3 factorial, it means there are how many terms in the numerator? 3 terms. So where is the 3 terms reaching? 1, 2, 3. 3 terms will reach there, isn't it? That is n minus 1 and n minus. So that will be n minus 1 and n minus 2. Then our x is raised to power what? Power 3, because x is what we have here, isn't it? Yes. So that was the expansion. So if you look at this expansion, ladies and gentlemen, you will actually see it is a Maclaurin series expansion. Because by the time we were dealing with the binomial theorem, we had not dealt with the power series, isn't it? So this is actually a Maclaurin series expansion, because if you have your function f of x you've been given is 1 plus x raised to power n, if you differentiate this function f prime of x, so it is the power times the coefficient. Are you seeing?
Yes.
Meaning it is n into 1 plus x, then you reduce by the power by 1. Are you seeing that? Then you reduce the power by 1. Then you move to the next one. If you differentiate it for the second time, you get n minus 1 times n. You get n into n minus, then you now have your 1 plus x, you reduce the power by 1, you get n minus 2. See this? Because you see, I'm not going to the inner function, because if I differentiate the inner function, I get 1. No, those are now things you know as we will be talking about, isn't it? Because you must differentiate both outer function and inner. Yes, so the moment you differentiate the inner function 1 plus x, you will get 1. When you differentiate once, you get 0. When you differentiate x, you get 1. See, it means the derivative of the inner function is 1, meaning it is not important to us, isn't it? Because 1 times anything, it will remain that thing. Are we together? Are we together? Yes. Then you move again. If you have f triple prime of x, it is the power times the coefficient, isn't it? You will have n into n minus 1 into n minus 2, then your 1 plus x, you reduce the power by 1. So it will be n minus 3, isn't it? Now after that, we now have all this. So in the Maclaurin series, what do we have? We have f of zeros, isn't it? Are we together? So you start, what is f of 0? F of 0 is where there is x you put 0, isn't it? So where there is x you put 0. If you put 0, so you remain with 1 raised to power n. So 1 raised to power n is just 1. Then you move to the next one, f prime of 0, where there is x you put 0, so you will have f prime of 0. Will be what? See, you put 0 where x is. So you remain with 1 raised to power that. So 1 raised to power anything is just 1. So what will you remain with? N. Then you move to what is f double prime of 0. See where there is x you put 0. See where there is x you put 0, you remain with 1 raised to power that. 1 raised to power anything is 1. So you remain with n into n minus 1, isn't it? So even if I reach there only, what is the Maclaurin series expansion of a function f of x? A function f of x, if you want to expand, you start from f of 0, isn't it? Then plus f prime of 0. If it is prime, it means it is over 1 factorial, then your x is raised to power. Then after f prime of 0, you move to f double prime of 0. If it is double prime, it means it is over 2 factorial, then x is. So see, what is f of 0? F of 0 is 1, meaning this is 1. What is f prime of 0? F prime of 0 is n. What is f double prime of 0? F double prime of 0 is n into n minus. So if you look at this, you'll actually see it's the same thing we were doing here. So it means that binomial theorem we were dealing with in the first module, it was actually the Maclaurin series expansion. Are you seeing that? So that is the Maclaurin series to expansion of a binomial expansion, isn't it? The problem itself is what is referred to as a binomial expansion, isn't it? So you are using Maclaurin's theorem without necessarily knowing it. So what I was doing here is just an algorithm, a means of mastering a formula, isn't it? You don't always need to go into details when you want to master a simple concept. You just need to have an algorithm of mastering a formula. So that was actually a Maclaurin series expansion, and we ended up with that. Now, this binomial series is actually the polynomial resulting from the finite difference formula. Now, from our finite difference formula, the interpolation polynomial, that interpolation polynomial is given by this. Our x is now the change, that delta. So in the finite difference formula is given by, if you want to expand a function f of x, it is given by the binomial theorem. If you have 1 plus x, our x is now the deltas, the differences. 1 plus delta raised to power. Now our n, we are going to use p instead of n, then the f outside. So the f, when it is the forward difference formula. Are we together? So when it is the forward difference formula, we will be noting as f naught to f forward for the forward difference formula. Are we together? So the forward difference formula is just this binomial. So this our x for the forward difference formula is the changes the deltas. Then n we shall use p. We'll see how to get that p. Okay? We'll use p instead of n, meaning where there is n in this problem, you will be putting p. Where there is x in this problem, you will be putting delta. So you will see this will be delta raised to power 0, which of course is this. Are you seeing that? Then you can see here is delta raised to power. Delta raised to power 0 is this, because it's not there. Anything raised to power 0 is 1, isn't it? Are you seeing that? So delta raised to power 0 is actually here. You will see when I expand this. Now look at this. If you expand 1 plus delta raised to power p, then f naught, what do you get? Meaning where there is x is now being occupied by the delta. Are you seeing that? And where there is n is now being occupied by p, because power is now p. Remember, power here is n, here we have x. So we are just substituting. Are you getting? So let us start substituting. 1 plus x raised to power n, we add this. So look at this. 0 factorial is 1, x raised to power 0 is 1. Meaning this term, the whole of this term is always 1. Then here 1 factorial just 1, x raised to power 1 is just x. So n times x. Meaning the first two term is always 1 plus nx. Are you seeing that? Are we together? So the first term, you come and write your first term here is 1 plus your second term is n times x. But your n is what? And your x is what? Delta. Are you seeing that? So it means here it is p delta. Then the next one is n into n minus 1. And your n is what? P. So it is p into p minus over what? Then your x is what? Delta square. Are you seeing what is happening? Then you move to the next one here. Your n is p. Where there is this n, you put p, isn't it? Are we together? So if you put p there, you are going to have p into p minus over 3 factorial. Then your x is what? Where there is x, we have delta cube. Then outside, what do we have? F naught for denoting for the forward difference. Are we together? So you can see f is outside the bracket, meaning it is a common factor of everything inside. Are you seeing that? It is a common factor of everything inside. Now, do you get what I'm saying? So this f naught is a common factor of everything inside. So you bring it inside. What do we now have? F naught times 1. So this side we are expanding f of x. F naught times 1 is f naught, isn't it? Then you move f naught times this, you have plus p, then delta f naught. Because f naught comes in front here. Umeona? Then it is delta f naught. Then you move again. F naught times this, so you have it is p into p minus 1 over 2 factorial. Then we have delta squared, then f naught has come in front of it. So the second difference, and these differences are for the f. So you see the reason why I was not putting the f, because there's an instance when you'll be using the backward difference and the instance when you'll be using the forward difference, isn't it? Are we together? Yes. Then next, f naught, if you multiply here, what do you have? Plus p into p minus 1 into p minus 2 over 3 factorial, then delta cube f naught, meaning the third column. Are we together? The third column, meaning here, if you are now going to deal with f naughts, you go back to your forward difference formula. If you are dealing with the f naughts, you can see f naught will now be this f naught. Then here you have your what? Are we together? Your delta f naught, delta squared f, in that order. If you're dealing with the backward difference formula, we shall see how to denote the backward difference formula, okay? So if this was now a backward difference formula, if you've already constructed it like this in case of a forward difference formula, in a backward difference formula, you'll now be using the negatives to indicate for the backward difference formula. If instead of f0 for the backward, you now start with the -1, -2, -3, in that order. We shall see how to do that later. So that is the forward difference formula. So it means what is left, how do we get, because we know our changes, we know our finite differences, we've already found from the table, isn't it? We've already found the finite differences. After finding the finite differences, it means all we need to know, how do we get this p? Are you seeing that? So that is now the big deal. How do we get that? The P. Okay? Now getting P is very simple. To get that P is very simple. First of all, if you want to get a P because there's a case when you'll be looking for the polynomial and you use that polynomial to evaluate a certain value. But there's a case when you'll just be evaluating the value direct. Are we together? So getting that P is done like this. Let's say I want to use an example to make the different explanation. Let's say, for instance, you've been told to evaluate f of 1.5 or f of, let me use, or f of negative 0.5. Which one? F of negative 0.5. That is a good one. So you'll be told to evaluate f of negative 0.5. Are we together? So for you to evaluate f of negative 0.5, you check, where is negative 0.5? Negative 0.5 is between negative 1 and is between negative 1 and 0. So let me now use something general. Instead of this negative 0.5, let me see, for instance, I want to get the polynomial f of x. Are you seeing that? F of x. Now for you to get f of x very easily, for you to get this interpolation polynomial very easily, always look at an interval where there is 0, because something minus 0 will remain that thing, isn't it? So it is always easier to evaluate this polynomial at a point where you have 0. Are you seeing here I have x value 0 is here? So it means for you to get a polynomial you'll be using to evaluate, to interpolate any point, then it means you deal with the point which has 0. 0 is easier to work with. Whether you will be getting x minus 0, that will just be x. Whether you are having 2 minus 0, that will just be that thing, isn't it? Are you seeing that? So it means evaluating a function at a point where you have 0 is very easier. So if you are looking for f of x, let me now say I'm not looking for f of 1 or f of 2. I'm just looking for generally f of x. That is the first thing, isn't it? If you're looking for f of x, look at a point where there is 0. It's easier to work with. Okay? Are we together? So are you seeing here, I have 0 here. Are we together? So it means it is easier to evaluate it at this point. 0, 1. When the x value is 0, x value is 1. So the first one you denote as x naught, and this next one you get to be x1. So the x you are looking for is in the middle of x naught and x1. Are you getting the point? Are you seeing where we want to evaluate that function? Where we want to construct it to form that interpolation polynomial? Are we together? So we've let our x naught to be 0 and our x1 to be 1. We want to evaluate it at this interval. Okay? So here, x we are looking for is in the middle. So for you to get a p is always found like this. P is this x minus f of x naught. It is this x minus f of x minus x naught over h. H is the height, is the width, the interval. How do we get the interval? As we've said, it is always second minus first, or final minus initial. Are you seeing that? So it means when you are looking for the height h, the interval is from 1 minus 0, meaning the whole of that interval is what? 1 minus 0. What is the whole interval? Is 1, meaning that h tells you the whole of this interval. But now x is what we want. It is x from x, meaning you are saying like this. Here I have here x naught, and here I have here x1. Then I want x, meaning what is this length and what is this length. Are you seeing that? So it means P is just the ratio. P is the ratio of this length if you let the ratio of this length over the whole of that length. Are you seeing? So this length is now the x minus x naught, and the whole of this length is now the whole interval h. Are you seeing what I'm trying to imply? Are we together? Are we together? The whole interval you are evaluating is from there to there. That is the whole interval. But if you are looking for x from this point, meaning you are just looking for this interval over the whole interval. Are we together? Are we together? So we have P, we found is what? x minus x naught, and our x naught is 0. That's why we are saying it is good to use a point which is 0, because you now see x minus 0 is just x over 1. So it means p is what? Meaning where there is p, you put x. Are you seeing that? Where there is p, you put x. So where there is p, if you put x, you will find f of x is equals to what? F naught. What is the f naught? It is the first one. Are we together? At what point were you evaluating it? This is now what you do. If you are moving forward, you know, if you are from top moving downward, you are moving forward from the first value towards this side. So this means you are moving forward. Are you seeing? X negative 1, x 0, x 1, you are moving forward. And if you look at the finite difference formula, it means moving forward is like that, downwards, isn't it? Because for you to move from x negative 1, x 0, x 1, see x negative 1, x 0, x 1, meaning moving forward is going downwards. Are you seeing? Are we together? Yes. Then moving backward, you are coming from the largest value coming backwards, isn't it? And if you are moving backward, if you look at the finite difference table, meaning moving backward is like going up like this. Are you seeing what is happening? So when we are talking about the forward difference formula, meaning from this table we are moving forward from the first x value towards the last x value. Are you seeing that? Are we together? So here, I'm evaluating it at this point. So at this point where you are evaluating it, is where you come and you now put the line in the middle here. You know, you come and put a line, I'm evaluating it here. Because that is where you place your x. Have you seen where I placed the line? Because x was in the middle here. I've just say I've crossed it with the line, that x is here. Are we together? So this is where I'm evaluating the x. The x value is in the middle here, there. I'll place it with the line for that. Then after that, where are the finite difference moving forward? At that point you can see, from here you can see, when I read, the first finite difference is 2, 4, negative 4, 10. So you extend your line. That is the forward. Look at that. X value is in the middle here. You put the line for x value because we have the x and the f of x here at this point. So at this point, which finite differences do we get when I'm moving forward? See, I will start with the 2. Then from 2, see if I go to negative 4, it means I'm moving backward. But from 2, if I go to 4, see I'm moving forward. Are we together? Then if I'm at 4, see if I go to 8, it means I'm going backward. But if I move back to negative 4, it means I'm still going forward. When I'm here at negative 4, I can move to negative 12 or 10. So do I move to negative 12 or 10? I move to 10 because 10 is forward. Are we getting what I'm trying to say? Are we together? You are getting it? Yes, because moving forward is from the x small negative 1, 0, 0. You are moving in that direction. And moving in that direction, according to this table, is like moving downwards. Isn't it? Is that okay? Yes. So you've seen the point where we want to evaluate. Meaning when you now close with your line, you now come and start substituting the values. What is f naught? The first value of f. You're now using the forward difference formula. So if you're using the forward difference formula, it means this is f naught, f naught, f naught, f naught, f naught, f naught. Have you seen what's happening? Are we together? So that when you come, what is f naught? You go where f naught is there in your line. Under your line, where do you have f? It is 10. So it means this f naught is 10. Then it is plus. What is p? P you found to be x. So where there is p, you put x. Then it is x, then delta f naught. What is delta f naught in your line? 2. So this means it is 2x. Are you seeing what is happening? Are we together? Then you move again. Look here. What is your p? P you found to be? So it is x into x minus 1. So it is plus x into x minus 1 over 2 factorial. Then delta squared f. What is your delta squared f naught? In your line. In your line, where do you have it? 4. So it means there's 4 here. So what is 4 over 2 factorial? See, 4 over 2 factorial, it means when you simplify, you get 2. Are you getting that? So 4 over 2 factorial, if you simplify, you get 2. You move to the next one. Are you seeing that? What is your p? X. So we have x, it is plus x into x minus 1 into x minus 2 over 3 factorial. Then delta cubed f F naught. You go where you have delta cubed F naught. What is your value on your line? So I think the reason why it is better to put that line. Negative, negative 4. So it means here we have negative 4 there. So what is negative 4 by 3 factorial if you simplify? It means we have our f of x is 10 plus 2x plus 2x into x minus 1. Negative 4 by 3 factorial is? Calculator. Negative 2 over 3. You have negative 2 over 3. Then you have your x here, isn't it? X into x minus 1 into x minus 2. Have you seen? I've only reached where we are the cube, meaning when you are told it is a cubic polynomial, meaning the highest power of x they want is power 3. Meaning, see, we can still proceed. But we are not proceeding because they told us that f of x is a cubic polynomial. When they say f of x is a cubic polynomial, meaning they are expecting the highest power of x to be what? To be 3, because this binomial expansion, you will expand it up to that point you want it, isn't it? Are we together? So if you are told this is a quadratic polynomial, it means you will expand it where the power of x is 2. See, this is the point where power of x is 3, because we have x times x times x. See, that is x power 3. See, that is the highest term you've reached when x is power 3. When x is power 3, meaning it is only cubic when you reach here in the binomial expansion, isn't it? When you go forward past there, it is no longer cubic. Are you seeing that? It is now a polynomial of fourth order 4, isn't it? Or of the fourth degree, or degree 4, isn't it? Are we together? Are we together? So it means I've constructed this interpolation polynomial with the forward difference formula because I was moving forward. From this value towards the other direction, you are moving forward. And in the finite difference table, moving forward is like moving downwards. Are you seeing? Because the first x value is here followed by this, meaning moving forward is like moving downwards in the finite difference table, isn't it? So when I was moving downwards like that, that is a forward difference. So it means when I was at this point, then I now move upward like this. That is now a backward difference. So when it is a backward difference formula, instead of going to put f naught here in case of a backward difference formula, what are we going to put? We are going to put our f's of the negatives, f of negative 1, f of negative 2, f of negative 3, f of negative 4 to represent the backward differences. Are we together? But it means when we are constructing the polynomial from the binomial theorem, we use a case of a forward difference. So that when it is a case of a backward difference, it's going to substitute that note now, isn't it? Are we together? Yes. Good. So that is how to deal with the Newton-Gregories. That is how to construct the finite difference table. That is how to expand the binomial series on the Maclaurin series. And that is how to get the interpolation polynomial. You've seen what is important is that you have to know the binomial series, isn't it? After knowing the binomial series, you have to know how to get the value of this p, isn't it? And you have to know how to deal with it when it is talking about the forward difference formula. And you have to know how to deal with it when it is talking about the backward difference formula. Are we together, ladies and gentlemen? Yes. Can we now handle the first case in this Newton-Gregory interpolation formula?